In this video, we'll walk through the design of a rate limiter, a critical component in any scalable system, especially those that expose APIs or handle user-generated traffic at scale. The goal of a rate limiter is to control the rate of incoming requests to prevent the system from being overwhelmed. This becomes especially important in cases like preventing resource starvation during denial of service, DOS attacks, reducing infrastructure costs by limiting excess or abusive usage, and preserving service availability by avoiding server overload. Whether you're designing APIs, web services, or internal microservices, rate limiting plays a foundational role in ensuring fair use and system stability. In the next few slides, we'll clarify the problem, understand its context, explore several algorithmic techniques, and dive into a scalable system design suitable for distributed environments. The problem is to design a rate limiter to control the rate of traffic. The benefits include prevent resource starvation caused by denial of service, DOS attack, reduce cost by limiting excess requests, prevent servers from being overloaded. Here are some good requirement questions to ask. Are we designing a client-side or server-side rate limiter? What does it throttle requests based on? What's the scale of the company? Should the rate limiter work in a distributed environment? Let's break down the high-level components and considerations in designing a rate limiter for a scalable system. 1. Client-side versus server-side versus API gateway. Client-side rate limiting pushes enforcement to the user's application, often for fairness or cost saving. However, it's unreliable. A malicious or buggy client can easily bypass it. Server-side rate limiting is more robust and typically enforced per service instance or centrally, ensuring requests are throttled regardless of the client's behavior. A modern approach is to implement rate limiting at the API gateway, like Amazon API Gateway, Kong, or NGINX. This offloads logic from the services and allows for centralized management and monitoring of traffic limits. 2. Cloud microservices context. In cloud-native, microservice-based architectures, each service may need individual rate limits based on SLA, pricing tier, or traffic. You can have service-to-service rate limiting, where upstream services must throttle requests to downstream ones to prevent overload. It's critical to use a central store or distributed cache like Redis or Memcached to synchronize limits across instances. 3. Rate limiting algorithms. Fixed window counter, simple, but allows bursts at window boundaries. Sliding window log, more accurate, tracks exact timestamps, but memory intensive. Sliding window counter, approximation of the log with less memory use. Token bucket, allows for bursts, uses tokens to permit requests, ideal for APIs with occasional spikes. Leaky bucket, smooths traffic at a constant rate, good for shaping traffic flows. We're going to discuss some details of different algorithms in the next slide. In this slide, we'll walk through several common algorithms used to implement rate limiting in scalable systems. Each of these has its own trade-offs in terms of simplicity, burst handling, memory usage, and latency. 1. Token bucket. The token bucket algorithm allows for flexible traffic handling. Imagine a bucket that gets filled with tokens at a steady rate. Each request consumes one token. If the bucket is empty, incoming requests are throttled or rejected. This approach allows for short bursts of traffic, as tokens can be consumed quickly if needed. Pros: it's easy to implement and very efficient at runtime. Cons: the main challenge lies in tuning parameters like token refill rate and bucket size to match usage patterns. 2. Leaking bucket. The leaking bucket is similar in concept, but instead of refilling tokens, it processes requests at a constant rate, like a leaky pipe. Excess requests are queued, but if the queue fills up, new requests are dropped, even if they're more recent or critical. Pros: it ensures a steady processing rate and avoids bursts that overwhelm the system. Cons: during high traffic, old queued requests may be processed while fresher ones get dropped, which isn't always ideal. 3. Fixed window counter. In the fixed window counter method, time is split into fixed length windows. e.g., 1 second. Each request increases a counter. Once the count hits the threshold, all subsequent requests in that window are dropped. Pros: very simple and fast to implement. Cons: at the boundary of windows, a spike in traffic could let more requests through than intended, creating enforcement gaps. 4. Sliding window log. This approach keeps a timestamp log of each request in memory. For each incoming request, outdated timestamps are discarded, and if the remaining count is within the allowed limit, the request is accepted. Pros: it provides accurate rate limiting and smooth traffic handling without spiky enforcement. Cons: memory intensive, as every request must be logged, even the rejected ones. 5. Sliding window counter. This method is a hybrid of the fixed window and sliding log approaches. Instead of tracking every request, it keeps aggregate counts in overlapping time windows, e.g., partial contributions from adjacent buckets. Pros: smoother rate enforcement and more memory efficient than the full log. Cons: it's a good middle ground, but may not work well if strict per-request accuracy is required. Wrap-up. When choosing a rate-limiting algorithm, consider your system's tolerance for burstiness, memory constraints, and accuracy requirements. Token bucket and sliding counter are often favored for their balance of efficiency and fairness, but the right choice depends on your specific context. In this part of the design, we're diving into how the rate-limiting logic is actually implemented, using Redis as our backend store. First, when a client sends a request, it's intercepted by the rate limiter before reaching the application logic. This could be at the API gateway, a proxy layer, or a dedicated microservice. Redis is used as a high-speed, in-memory cache to track and manage request counts. Each user or client is assigned a unique key, for example based on IP or user ID, that maps to a counter in Redis. We use the incr command in Redis to atomically increment the counter for that client. If it's the first request in a time window, we also set an expiry for the key using the expire command. This defines our window size. The rate limiter checks the counter value. If it exceeds the allowed limit, we reject the request immediately and return an HTTP 429 response, meaning too many requests. If the limit is not reached, the request proceeds to the API server and the counter is incremented. The configuration rules, such as how many requests are allowed per minute per user, are stored on disk. This makes it easy to persist and manage rate-limiting policies centrally. These rules are regularly pulled into the cache, so Redis always has an up-to-date copy to enforce. Race condition handling. In distributed systems, race conditions are one of the trickiest problems in rate limiting. Here's a common scenario. 2 or more requests arrive concurrently at different servers. They read the same counter from Redis and think the request count is below the limit. They both increment it and allow the requests, unintentionally exceeding the limit. To solve this, distributed locks. You can serialize access using Redis-based locks, e.g., redlock. While effective, locks reduce throughput and introduce contention, especially at high QPS. Lua scripts in Redis. A more efficient and widely adopted method is to use a Lua script that combines the read, check, and increment steps into one atomic Redis operation. This eliminates race conditions without locking and is used by systems like Kong and NGINX. Sorted sets for sliding window. For more granular control, especially for sliding window rate limiting, we can use Redis sorted sets. Each request timestamp is added as a member. Old timestamps are pruned. Count of valid entries determines allowance. Synchronization between rate limiter instances. In production environments, rate limiting often runs on multiple servers for redundancy and scalability. These must share a consistent view of user request data, which is why we use centralized caches like Redis or Memcached. Redis supports atomic operations and has good support for TTLs, making it ideal for counters. All limiter nodes read-write to the same Redis instance or cluster. This ensures consistent enforcement regardless of which server handles the request. In some architectures, sharded Redis clusters are used for scalability, especially if there are hundreds of thousands or millions of keys being tracked. Performance optimization in multi-region setups. When your application spans multiple data centers or cloud regions, minimizing latency and replication lag becomes critical. Latency trade-offs. Reading/writing from a centralized Redis in another region adds round-trip delays. This delay may impact both request latency and rate limiter responsiveness. Local versus global Redis. You might deploy local Redis instances per region for low latency. Each handles rate limiting locally and syncs periodically with a central control plane or uses eventual consistency models. Eventual consistency model. For non-critical traffic, allow some leeway. Slight temporary overages in local regions may be acceptable. Use background jobs to reconcile counters or throttle aggressive users retroactively. Storage and config management configuration files, like limits per endpoint, user IP, are often stored in a database or config service and loaded into Redis periodically. This allows for dynamic updates without redeploying services.